Hello friends, I'm going to talk to you about a quantum mechanical problem called as particle in a box. In one of the earlier sessions, we talked about wave mechanics, and today's session happens to be an application of wave mechanics. So therefore, the session is planned as follows. That is, to begin with, I'll briefly recall what is wave mechanics. Then thereafter, I'll try to define what is this problem of particle in one-dimensional box. Having done that, we will see that how do we formulate Schrodinger wave equation for this system. Then we will solve the Schrodinger wave equation, and thereafter, once we get the wave functions, we will normalize them. Then towards the end, we will sum up what we do in this small session over here. Okay. Now, as regards wave mechanics, we know that wave mechanics is a science that deals with the quantum mechanical systems like atoms and molecules and things like that. In the sessions which we discussed earlier, we talked about wave mechanics to be a mathematical formalism for understanding quantum mechanical systems. And this basically is a mathematical approach to understanding these kind of systems. And this basically incorporates two very important phenomena which are the consequences of quantum mechanical nature of atoms and molecules. They happen to be de Broglie principle, that is the dualism of wave particles. That means the electron has to behave or can behave or does behave as a wave also. That means there is a particle as well as wave behavior shown by electron there. And second important consequence of quantum mechanical nature of atom and molecule is that is it must adhere to what's called as a Heisenberg's uncertainty principle. So this formalism, that is the wave mechanical formalism, incorporates both of these aspects over there, and this actually is based on certain postulates. We'll quickly recall what are these postulates, then we'll try to see then how do we use this formalism to understand the particle in one-dimensional box problem. Okay, and the postulates happen to be like this. The first postulate says that the behavior of a single particle is described as fully as possible in terms of something called as a wave function, which is represented as psi. That's the first postulate. That means if I'm talking about the behavior of an electron in an atom or an electron which is confined to an electron as a particle in one-dimensional box, that the behavior of that electron or that particle can be described as fully as possible in terms of something called as psi, which is called as a wave function. And the second postulate tells me that this wave function can be obtained by solving what's called as a Schrodinger wave equation, which is given as h psi is equal to e psi, and this h you see here is with a caret on this. This is called as an operator there. So h is called as an Hamiltonian. It's an operator for total energy there. And then this h psi is equal to e psi is the Schrodinger wave equation which we need to solve to get the wave function psi, which describes the behavior of particle in the system over there. In today's case, it happened to be particle in one-dimensional box. The first principle tells me that wave function has all the information about the system. The third postulate tells me how to get the information out of the wave function there. For that, what we do is we take a suitable operator, operate it over the wave function which you obtained by solving Schrodinger wave equation, and that in turn gives us the value of that particular property we're talking about. So if I want to know about the momentum of the particle, so what do? I have the wave function which has come to me from solving the Schrodinger wave equation. I operate this wave function over by an operator for momentum there. So what I get is the value of the momentum there. And the fourth postulate tells me about, gives some kind of a significance or meaning to the psi, because psi per se doesn't have physical significance, but the square of psi, that is psi square or psi into psi star, that happens to be what's called as it's a measure of the probability of finding the particle over there, or it's a measure of probability and it's referred to as probability density. And typically, as regards using this wave mechanics, that means this wave mechanics is based on these four postulates over there, which we just understood over there. And then these postulates are used in the following fashion. That means if I have to deal with any quantum mechanical problem using wave mechanics, what do I do is we follow a certain set of sequence over there, and that happens to be, that is, we first formulate the Schrodinger wave equation for the system in question. That means today we will do it for particle in one-dimensional box. Thereafter, we solve the Schrodinger wave equation and we get certain solutions from there. Like if we solve a quadratic wave equation, we get a solution from there. Then thereafter, we apply boundary conditions. We'll understand all this when we solve this problem about particle in one-dimensional box. Then the wave functions what we get, we try to normalize them. and that ensures that particle is confined to the system itself. And then we try to dynamic variables can be obtained from this wave function over there. So that is a general sequence of steps which we follow. That means you formulate Schrodinger wave equation, then we solve it, apply the boundary conditions there, get the wave functions, and then use them to get the information about the system there. Okay. Now let's come to today's problem. Today's problem happens to be particle in one-dimensional box. Let's understand what is this problem. In fact, this is the simplest possible quantum mechanical system we can deal with, and this happens to be a model system. We cannot have a particle confined to one-dimensional box per se, but this is a very good approximation to understand that how does this wave mechanics operate, because that's the simplest system to understand there. Let's try to now define what is understood by when we say particle in a one-dimensional box. Okay. Now essentially what we have is to understand, to visualize particle in one-dimensional box. When we say one-dimensional box, so there are three dimensions we know of: x dimension, y dimension, z dimension, and today we are talking about a particle which is confined to an x dimension there. That means I am ensuring that my particle moves only along the x dimension over there. And to make a hypothetical box, what do? I erect some kind of imaginary walls at x is equal to 0 and x is equal to a. So, and these walls happen to be having a potential equal to infinity. Also, I ensure that at any region below 0, the value of x less than 0, again the potential happens to be infinite. Similarly, at region 3, which is values of x greater than a, again the potential happens to be infinity. That means from 0 to a, that on the x dimension, potential could be anything, and we take it to be 0 so that it becomes simpler to understand over there. So essentially what I am doing is I have erected two boundaries over there at x is equal to 0 and x is equal to a, and since they are of infinite potential, the particle cannot go out of this. That means the particle is forced to remain from 0 to a. So that is the meaning of particle in one-dimensional box. We can say that the potential v is equal to 0 when x is greater than 0 and less than a, and is equal to infinity when x is elsewhere. That means at the boundaries and also either below 0 or above a. So that is the system I am dealing with. That is my particle in one-dimensional box. That means I am forcing my particle to be confined in the region from x is equal to 0 to x is equal to a. It cannot be at 0 or a, it has to be between the two, and it can be anywhere behind this also, beyond these two also. Okay. Now if this be my particle in one-dimensional box, then the next step is I have to formulate a suitable Schrodinger wave equation for that. And let's see how do we do that. Now Schrodinger wave equation we know is nothing but h psi is equal to E psi, and we just mentioned that this h is an operator for total energy, that is called as Hamiltonian, and the total energy of a system happens to be sum of the two energies, that is the kinetic energy and the potential energy. And for kinetic energy, the operator is given a symbol as T caret over there, and V caret is the potential energy operator over there. So in fact when I say to formulate Schrodinger wave equation, essentially we have to formulate expression for h, that is the Hamiltonian, and that in turn happens to be equal to T plus V. So to formulate Schrodinger wave equation or to formulate the Hamiltonian, we need to formulate the operator for T and V over there. Let's see how do we do that. Now as regards the operator for kinetic energy, that happens, we know that kinetic energy is the classical expression for that happens to be half of mv square, and since we are talking about the motion of particle along x dimension, so we put a qualifier over there, that is mv x square. So that I can simplify by just multiplying and dividing by m. I can get the 1 by 2m m square vx square, and this mv can be replaced by momentum, that is px there. So this is the classical expression for kinetic energy. To make a quantum mechanical operator there, what do? Is we substitute the quantum mechanical operator for the momentum over there, and that happens to be minus iota h cross d by dx. When I do that, I get an operator for T, that is the kinetic energy, and that operator happens to be minus of h cross square by 2m d2 by dx square. So that is the quantum mechanical operator for the kinetic energy there. Now as regards the potential energy goes, inside the box we have taken that potential energy V happens to be 0. So the operator will be state as 0 over there. So the Hamiltonian now becomes minus of h cross square by 2m d2 by dx square plus 0. That is the kinetic energy part of it. This is the potential energy part of it. Since this is 0, so essentially Hamiltonian happens to be equal to the kinetic energy operator over there. Okay. if this be so, then if I just take minus h cross square by 2m d2 by dx square, put psi x over there to be equal to ex, so that is my Schrodinger wave equation there. I can simplify it by taking this term over there, minus h cross square by 2m on this hand side. On the right hand side, what do I get is d2 by dx square of psi x to be equal to minus of 2m by h cross square psi x. And then when I simplify, I get the following expression over there. So this is the Schrodinger wave equation for particle confined to a one-dimensional box of the length equal to a. That means confined from movement from 0 to a along the x-axis there. Now, if I go further and see what happens outside the box. Outside the box, what do we have? We have just defined our system to be such that outside the box, that is on the boundaries and out of the boundaries, we have V to be equal to infinity. So my operator for V, that is the potential resistance operator, happens to be infinity. I just substitute over there as before, and then I just do a little simplification. I get the Schrodinger wave equation to be d2 by dx square of psi x, and so on and so forth there. So essentially what I've done is I have been able to formulate Schrodinger wave equation for the particle in the box and also outside the box. That means in the box, if you just see with the way we defined our particle in one-dimensional box, which are there are three regions there. One below 0, 2 was within the box, and third region was beyond A. Okay, so in the region 2, that is in the box, that is of interest to us, and outside the box again, but we will try to just see what do we get from there. Let's try to see, since we have got now Schrodinger wave equations for the three regions there, that means for region inside the box, that is region 2, and outside the box, that is region 1 and 3 put together. Now when we solve this expression, let's see what do we get. When I solve Schrodinger wave equation for particle in the region 1 and 3, let's see what do we get here. So this is my expression over there. That's what we just drove as an expression for Schrodinger wave equation there. And since E, the energy of the particle, happens to be negligible as compared to infinity, anything is negligible as compared to infinity. When I do that, I get the following expression there, which is a simplified one over there. And if I just take infinity on left hand side, I get psi x to be equal to 0. What does it mean? This means that the wave function doesn't exist. That means the wave function is 0 for the region 1 and region 3, which is exactly what we want, because we do not want that particle to be outside of the box or in the even on the boundaries of the box, because the potential happens to be infinity. That is exactly what I'm getting from solving the Schrodinger wave equation for particle in the region 1 and 3. Okay. Now that is not of interest to me. What is of interest to me is region 2. Let's see how do we deal with the region 2. That is of interest to me, and let's see what do we get here. In case of region 2, what do we see? That this is the expression I have for my Schrodinger wave equation, that is d2 by dx square of psi x plus 8 pi square m by h square e psi x is equal to 0. Now this is a little complicated equation, but we can simplify it by just seeing that this whole thing is a constant here. 8 is a constant, so is pi, mass of the particle is constant here, so is energy, and h is a Planck's constant over there. If I just take all this and substitute it equal to alpha square, if I take this whole term other than psi x to be equal to alpha square, then I get expression to be d2 by dx square of psi x plus alpha square psi x to be equal to 0. This is a standard differential equation of second order, because I have purposely taken it to be alpha square so that I can get a standard form of differential equation whose solution is known to me. Okay, so I could have substituted in some other way also, but that will not help me. So I have purposely taken this whole term to be equal to alpha square. When I do that, I get expression which is solvable there, and the general solution of this particular expression happens to be psi x to be equal to a sin alpha x plus b cos alpha x. So that is a standard differential equation and a standard solution to that one there. Okay, so far where we are, we have formulated Schrodinger wave equation for particle in the box, that is in the three regions there, region 1, 2 and 3. 1 and 3 we have seen that particle cannot exist there. That is exactly what we wanted. Now in region 2, what I have done is I have taken the Schrodinger wave equation, simplified it by making small substitution over there, and I get a standard form of differential equation which I solve. I get a standard solution there. Okay, so far so good. But now what do we do next? Because if you just see, when we just formulated the sequence of events to be done to apply the wave mechanics to a quantum mechanical system, we know the next step happens to be, that is, this wave function which I have got as a solution of Schrodinger wave equation must adhere to the boundary conditions. And the boundary conditions in this system happens to be the following. That is, the first requirement is that when at x is equal to 0, because the potential happens to be infinity, the wave function must go to 0. Similarly, the second boundary condition is that when x is equal to a, there again, since potential happens to be infinity, wave function must go to 0. So these are two boundary conditions which we have to apply on this wave function, which we got as a standard solution of the differential equation we have been able to formulate there. Let's see what do we get. Now, when I apply my first boundary condition, the first boundary condition happens to be, as just mentioned, that at x is equal to 0, psi must be equal to 0. If I substitute over there, that is, this psi x happens to be 0, to be equal to a sine alpha 0, that is, I am just substituting 0 for x. Similarly, b cos alpha, this is again x is equal to 0. When I do that, what do I get? I get a sine 0, and sine 0 is 0, we know that, it comes over here. And cos of 0 happens to be 1, so that I get it b over here. That means 0 is equal to b, or you can say b is equal to 0. That is one thing we get by applying my first boundary condition. That means I have got a wave function, but the moment I apply my first boundary condition, that can be met, or that is can be satisfied if and only if the parameter b happens to be 0. When I do that, now my wave function comes out to be psi x to be equal to a sine alpha x. So that is my wave function now. That means this is the wave function. The wave function I got earlier, that is, this wave function was the one which came as a standard solution of the differential equation I had there. The moment I apply boundary condition, I get this my wave function. So this is the wave function which is the solution of the Schrodinger wave equation. Also, it adheres to the first boundary condition. Then what do I do next? I apply the second boundary condition. When I do that, that is, the second boundary condition happens to be that at x is equal to a, psi must go to 0. And when I do that, I apply on this particular wave function, I put psi x to be equal to 0, and that is really a sine, and for x I put it as a. So that means a times sine of alpha a happens to be equal to 0. Now there are two possibilities. Either a happens to be, means this expression can be true if and only if either a is 0 or sine of alpha a is 0. A cannot be 0. If a is 0, our wave function becomes 0. Particle cannot exist. So by logic we can say it must be true, that is, sine alpha a must be equal to 0. That is what we get by forcing our wave function to follow or comply with the second boundary condition. When I do that, what do I get? What do I get? That alpha a to be equal to plus minus of n pi, because sine can be 0 only if this part of the sine, that means the theta part of it, happens to be equal to n plus minus n pi. For any other value of sine, there will be some value there. It won't be 0. Okay. So by this what I get is, I get alpha to be equal to plus minus n pi by a. So that is the expression, that is the information I get by, because I have substituted something over there, alpha square to be equal to 8 pi square, so on and so forth. Now, by forcing my wave function to comply with the second boundary condition, I find out that is this alpha a should be equal to plus minus of n pi, or we can say alpha to be equal to n pi by a. So that is what I get from here. So this I substitute back, so that gives me the wave function over there. The wave function will be now psi x to be equal to a sine of n pi by a. That means for alpha, I have just made a substitution over there. That is what I got earlier in the previous slide over there. That is n pi by a x. So this is the wave function. Now what is the qualification of this wave function? This wave function is the one which is a solution of the Schrodinger wave equation we formulated, number one. Number two, it adheres to the first boundary condition, and also it adheres to the second boundary condition. So that means this is a set of wave functions which are the solution of the Schrodinger wave equation of particle in one-dimensional box. Also we see here that is that n can have a value of 1, 2, 3, 4 up to infinity. What does it mean? This means that we have got a series of wave functions. All of them happen to be the solution of Schrodinger wave equation. And we will see more to the meaning of this one when we say n. And this n happens to be a quantum number which is called as a, which has a significance when we talk about the energy expression. We'll talk about that little later. Okay. So So these are the wave function which satisfy both the boundary conditions. So what do we do next? What do we do next is, that is, the wave functions we got, we must have a normalization of that one. What does it mean? What does it mean is the following. Because we know that the way we have defined our system, we have got a single particle. A particle is confined to a box of a dimension A, that is from 0 to A. Now, if the particle is somewhere in the box, that means my wave function should be such, because if you remember that the fourth postulate told me that is the square of the wave function is a measure of probability. That means now this wave function, if I take the square of that, means take the wave function, multiply by the complex conjugate of that and try to evaluate that, that must give me a value to be equal to 1. Because since it is a probability of finding particle, so I have the whole region from 0 to A. Particle could be here, here, here. It has certain probability here, certain probability here, and so on and so forth. All probabilities must add to give me 1. And that is the meaning of normalization. And that's the way how do we do it? Let's have a look at it. So normalization by definition happens to be something like this. That means you have a wave function psi x, and then also we have got the complex conjugate of that happens to be psi x star, and then we must integrate this wave function over the whole space. In this case, it happens to be from 0 to A. That's the limits of my box over there. And this, when integrated over the whole space, this should be equal to 1, which ensures that my particle is confined to it is within the box, somewhere in the box there. Okay. So that's the expression we got from our psi x to be equal to plus minus of A sine of n pi by Ax, and the complex conjugate of that happens to be, that is A star, because this part is real part only, even only A could be either real or complex part of it, so that will be multiplied by a complex conjugate of that. And when I put that together, I get that is to be equal to 0 to A sine, I just substitute over there, and when I simplify it here, what do I get is the following, A into A star, 0 to A sine square, so on and so forth. This expression I get to be equal to 1. When I solve it using simple trigonometry and the integration part of it, when I get that this A, that is a constant over there, because we had the wave function has come out as A sine of n pi by Ax. So this A, which is the prefix of the wave function over there, that must be equal to square root of 2 by A. So that is what I get there. And when I substitute over there, so what I get is psi to be equal to plus minus of root 2 by A sine of n pi by Ax. So this is the normalized wave function. Now, what is this wave function? How is it different from the previous ones there? This is a wave function which is a solution of the Schrodinger wave equation, number 1. Number 2, it adheres to first boundary condition, also the second boundary condition, and thirdly, it also is normalized. So this is the target wave function what we try to work out for any system there. So in this case, for particularly one-dimensional box, the solution which attempted to find out happens to be the following wave function there. Now, let's try to sum up what we have done today. So far, what we've done today is that we started by recalling what we did in the previous session. That is about, we just briefly recalled the wave mechanics, a science, a formulation which can be used to study quantum mechanical systems. And then we did recall the 4 postulates of wave mechanics, and also the general strategy of using wave mechanics to solve a quantum mechanical problem. Thereafter, we defined our system, that is the particle in one-dimensional box. That means a particle which is forced to confine itself to move in one dimension, that is x dimension, and also from stay within the limits of 0 to A, that's the length of the box. Then thereafter, we solved the Schrodinger wave equation, we formulated Schrodinger wave equation by substituting, working out the expression for kinetic energy and potential energy, and substituting by suitable quantum mechanical operators there. Thereafter, we got the wave function, wave equation, and that wave equation we solved for the region 1 and 3, that is on the boundaries and outside the box. We found that psi happens to be 0, that means the particle cannot exist over there. Thereafter, we came around to the main theme of today's session, that is solving the particle's behavior, or trying to understand the particle's behavior when it is in the region 2, that is within the box. Then we solved the Schrodinger wave equation, we got a generalized equation, got a general solution, applied first boundary condition, thereafter we applied the second boundary condition, we got a set of wave functions over there. Then towards the end, we try to normalize the wave function, and in return we have been able to achieve what is called as a set of wave functions which are normalized and are a solution to the particle in one-dimensional box. In the next session we will go further into this and try to see that what kind of energy expression we can get from the same treatment, and also we will try to visualize that how do these wave functions look like and what do they convey to us about the behavior of particle in one-dimensional box. Thank you.